So I've been promising to talk about this. MPI was developed in the era of single core processors, less than a core per chip. In fact, some of the early machines, the floating point was on a completely separate chip. MPI runs fine on modern multi and even many core processors, but your intuition or the way you think about it, the way your execution model, particularly your quantitative execution model, thinks about communication, may need to be changed. And so the sort of the classic model for performance in message passing looks like this. So we've got a latency. I use S for startup time and an inverse rate and the number of words or bytes. Let's use bytes. So that's the time. And that worked great. There are other models that have added other effects, but by and large, this has worked really well for a long time. And in fact, it still works very well for two processes communicating between, say, nodes. We'll look at the communication rate per process with different numbers of processes communicating between two nodes. So I've got two multi-core nodes, and I have one process here communicating, doing just a ping-pong exchange to a process on this other node. And then I do 2 to 2, and 3 to 3, and 4 to 4, and so forth. So if this model is correct, the rate per process should be independent of the number of processes, right? Because there's no number of processes in here. And what we see is yes and no. So down here, this is the message size. So for relatively short messages, it's a very good match. Right? The amount of time, basically the same, independent of the number of communicating processes. But as the messages get larger, it fans out like this. And that just doesn't match that model. This is the Cray XE6. This is a blue gene Q. In some sense, this is even prettier because it's really, really nice here. There's this thing. This is the transition between the eager approach, just send the data, to the rendezvous approach where send a request to send the data and then wait until I'm given permission to send the data. And it's fine out to about here, and then again we get this big fan out. Okay, so what is going on here? So we need to be thinking about, again, we have to have this mental model or execution model of what the machine looks like. Well, the machine sort of, the Cray sort of looks like this, and the blue gene in the case where one node is sending to the same other node also looks roughly like this, is that I've got my node, and it's got a bunch of cores, and each core has a process, and they're all sending to some network interface, which is then sending to another network interface that sends off to the MPI processes. So note, I didn't have this process. I didn't have an arrow between these two processes. Right? The model that says you've got a startup time and a latency times the message length just sort of assumes that there's enough resource for this process to talk to this process to talk to this process, and so forth. Where in fact, that's not the way these systems are organized. And the machines that are coming look much more like this than they look like the current blue genes. So let's assume that each sort of link in that system can support a certain rate of communication. And again, the data is going to be pipelined. And also assume that the overhead, sort of latency terms, are completely parallel. In other words, essentially the latency is all stuff that's done on each of the cores. Okay. Now that's an oversimplification, but you'll see that that's an oversimplification that works really well. Okay. So we've got this sort of model, but if we look at rates as we add processes. So here, different colors here indicate different lengths of messages. This indicates different numbers of communicating processes. What you see is that as I add processes, the amount of time it takes me to communicate the data, so actually this is the rate that I sustain, that rate goes up and then it flattens out. Right? And now this is on our Cray XE6. This thing is about 5.5 to 6 gigabytes per second. Okay, and so this is about 5.5 gigabytes per second. And this is very suspicious. Okay, and so what we see is that once I have more than a couple of MPI processes attempting to communicate at the same time, I run out of ability to get off the node. Right? Each process can communicate. Here, the process is doing about 2.8 gigabytes per second. After I get more than a couple of processes, I'm sending at nearly 5.5 gigabytes per second. If I have more processes, there just isn't enough capacity to get the data off in time. Okay? Now, even down here, I don't really pick up quite the double. These are, again, for fairly large messages. But for small numbers of processes, it's not too bad. OK, so what does this mean? Well, we can think about this in terms of what's going on. So we're going to assume that the sustained communication rate is limited by the maximum of any shared link. So that's that shared link and the maximum or the aggregate rate among all the links that could run concurrently. So if I go back to this picture, there's this link plus the aggregate of all of these. Okay, so that ends up looking like this. So instead of having an S plus N times a rate, I have a K, so number of communicating processes, but I also have a K over here. And I have a minimum of K times this rate, and which is the rate from each core to the NIC, and the rate between the NICs. Right? If this is really large, so I have a really fast network, then this eventually becomes infinity. And then I have S plus Kn over Kr, which becomes S plus N over R, which is the usual model. Right? But if this is not infinity, and if you look at the next generation of exascale machines, this is not necessarily much better than the current generation of machines. On those really fat nodes, this is going to be a real challenge. Okay. There are some refinements you can do. You can say, well, if I think about what's going on, if one process is communicating, it's pretty easy on the implementation. Once multiple processes are communicating, it may have to mediate among them. Maybe the rates aren't as effective. In fact, we do see that effect. But I will say that in terms of thinking about how you might think about designing your algorithms, this model, which merely adds one more term, so we had the S and the R, now I've got a second R, does quite well, and you'll see some examples. So again, looking at a Blue Gene Q and the Cray XE6, XE6 actually has an even more complicated structure. There's one NIC shared between two nodes. And I have a test that essentially finds a way to find processes on two separate nodes, then runs tests with varying number of communicating processes, one up to the number of nodes. There are some things you can't control. So the hardware, for example, may route messages longer ways around the network if it discovers that the network is congested. And so there's no way to really stop that. You just sort of measure that. And so here are some examples. I drew these from a paper that's going to appear at Euro MPI next month. And the code is available, although if you'd wait a week, there will be a better version of the code available. But the code is available now and runs. And so first we could do some fits to the data. Let's just look at the rendezvous regime. So remember, in those graphs, the short messages, things actually seem to work. And we see that here is, say, that effectively the network bandwidth, the internetwork bandwidth is effectively infinite, that it's not the thing that limits the performance. But when I'm in the rendezvous regime, it's not infinite. It's 5.5 gigabytes per second. And the performance of a single core to the network is 3.6 gigabytes per second. So by the time you have two processes trying to communicate at the same time, you don't have enough bandwidth to support them. And what that means is if you do I receives, I send, wait all with no work in there, it's going to be inefficient because the processes are only going to get in the case of the Cray, 1/16 of, you've got 16 processes running on the node, 1/16 of this 5.5 gigabytes per second. Strangely enough, that's actually pretty close to the numbers that you saw in those tables that I just showed. Right? So how well does it work? Well, here is measured data. So this is the number of communicating pairs and the message length. And this is the aggregate effective bandwidth. So as I add processes, I would like the aggregate to add up. And this is what we get with the 3-parameter model. So you can see there's a little bit of difference, but that's an excellent fit. If instead we look at the 2-parameter model, you get that. And that's not too bad down here, where the behavior can ignore the network interconnect. But it is terrible out here. In particular, it overestimates the aggregate bandwidth by more than an order of magnitude. And so if you're thinking about analyzing or understanding your code running on an SMP, you really can't use the simple 2-parameter model anymore. Here's some, so this is a table that shows the error. So this is the message size in bytes, the number of communicating pairs. This is sort of a color bar. The fit is actually quite good. The relative error here is still fairly small. It's about 0.25. If you look at the 2-parameter model, this is not the same color. This is a factor of 7 off. Right? So the fact that this looks sort of bluish here, almost all of this is a higher error than in here. And so we looked at this on a number of other networks. So on an InfiniBand connected cluster, again, the 3-parameter model fits pretty well. The 2-parameter model grossly overestimates the performance at the large message size. On the BlueJean Q, the fit's not quite as good. It turns out that that's because you need to take into account some more of the contention and parallelism here, so that the measured data here is the performance is a little better. You can make the formula a little more complicated and get a much better fit, but again, this is actually still a pretty good fit. This is the worst case here is only about twice as bad as in the case of the Cray, and neither of those is very bad. And so in particular here, by using a slightly different formula, we're able to capture this sort of sharp edge here and get a good fit. And then there was even a network we had access to at Cisco, which has a different structure and somewhat strange behavior, but this still captured it fairly well. So this sort of simple model is a much better one with which to work. So I'm going to encourage you to stop thinking about just the simple 2-parameter model, start thinking in terms of the 3-parameter model. In the case of blue genes, when you're doing halo exchanges, the important thing is the number of processes communicating over the same link. So if your processes are communicating one per link, taking advantage of the topology of the blue gene, then you're usually fine. And that's, again, what the data I showed earlier illustrated. But if instead you're having multiple processes communicating in the same directions, because, for example, you have a more complex topology, then this starts to apply. You can also then say, well, how do I deal with that? Well, you can take advantage of communication-computation overlap to cover some of this. And if we look at that, so here I set them, again, this is a benchmark, so I set the benchmark up so that the message size is about 1/10 of the amount of data that I compute on as a sort of computation load. And this graph shows the performance advantage of using the overlap. So 1, which is here, is no advantage. Less than 1 is a loss in performance. And this up here, which is 1.5, is like a 50% advantage. And so, and then this is the number of communicating processes. So for small messages, the overlap costs you. And so that's in some ways not so surprising. To start with, for small messages, the network is fast enough, and so there's nothing really to hide. You're getting the full performance out, and then you're getting sort of extra overhead of dealing with the complexity of that. So you sort of drop off. Here at about 10,000 words, you're starting to get some benefit, and that rises to like a 50% benefit with 16 processes at fairly large messages. So I'm not sure. Your mileage may vary. It depends on exactly how you got it laid out. But on a blue gene, you do get a benefit. And on the Cray, you get a benefit. Here, you don't pay much of a penalty. So there's almost no cost to doing it in the example that I ran. And as the messages start getting larger, you again start getting a benefit. This is a benefit up to, this is a factor of 1.7. So pick up a fair amount. There is an interesting drop-off at very large messages, which I haven't chased down. But the general message here is I can use an overlap in communication computation to cover the fact that I don't have enough bandwidth out of the node to stop the processes from essentially waiting to move data to become inefficient. Okay, so again, we think of this by forming an abstract model of how the machine works, give it a simple performance model, see how it matches reality. So reality is more complex than this. As I mentioned, there's a number of other terms that you can add to these formulas to get better fits. What's interesting is that one single parameter gives you a much better notion of what's going on. Again, I do want to emphasize these systems are very complicated, and so you really can't predict everything, and the fact that you can't predict everything should not stop you from predicting what you can. And so I think we've gotten a lot of insight in what's going on by looking at this data without worrying about some weird behavior. Okay, so really encourage you, as you start thinking about understanding the performance of your codes, to use this model instead of the simpler model with only 2 terms. It's really not much harder to use. In many cases, the term will drop out. So for messages that are short enough, it'll turn out that this term has no effect. But for longer messages, it can make a huge difference, as we've seen for the Crays over an order of magnitude.